The many-worlds interpretation is an interpretation of quantum mechanics that asserts the objective reality of the universal wave function and denies the actuality of wave function collapse. Many worlds implies that all possible alternate histories and futures are real, each representing an actual world. In lay terms, the hypothesis states there is a very large, perhaps infinite, number of universes, and everything that could possibly have happened in our past but did not, has occurred in the past of some other universe or universes. The theory is also referred to as MWI, the relative state formulation, the Everett interpretation, the theory of the universal wave function, many universes interpretation, or just many worlds. The original relative state formulation is due to Hugh Everett in 1957. Later, this formulation was popularized and renamed many worlds by Bryce Seligman DeWitt in the 1960s and 1970s. The decoherence approaches to interpreting quantum theory have been further explored and developed, becoming quite popular. MWI is one of many multiverse hypotheses in physics and philosophy. It is currently considered a mainstream interpretation along with the other decoherence interpretations, collapse theories, and hidden variable theories such as the Bohmian mechanics. Before many worlds, reality had always been viewed as a single unfolding history. Many worlds, however, views reality as a many-branched tree, wherein every possible quantum outcome is realized. Many worlds reconciles the observation of non-deterministic events, such as random radioactive decay, with the fully deterministic equations of quantum physics. In many worlds, the subjective appearance of wave function collapse is explained by the mechanism of quantum decoherence, and this is supposed to resolve all of the correlation paradoxes of quantum theory, such as the EPR paradox and Schrödinger's cat. Since every possible outcome of every event defines or exists in its own history, or world outline. Although several versions of many worlds have been proposed since Hugh Everett's original work, they all contain one key idea: the equations of physics that model the time evolution of systems without embedded observers are sufficient for modeling systems which do contain observers. In particular, there is no observation-triggered wave function collapse, which the Copenhagen interpretation proposes. Provided the theory is linear with respect to the wave function, the exact form of the quantum dynamics modeled, be it the non-relativistic Schrödinger equation, relativistic quantum field theory or some form of quantum gravity or string theory, does not alter the validity of MWI, since MWI is a meta-theory applicable to all linear quantum theories, and there is no experimental evidence for any non-linearity of the wave function in physics. MWI's main conclusion is that the universe is composed of a quantum superposition of very many, possibly even non-denumerably infinitely many, increasingly divergent, non-communicating parallel universes or quantum worlds. The idea of MWI originated in Everett's Princeton Ph.D. thesis, The Theory of the Universal Wave Function, developed under his thesis advisor John Archibald Wheeler, a shorter summary of which was published in 1957 entitled Relative State Formulation of Quantum Mechanics. The phrase, many worlds, is due to Bryce DeWitt, who was responsible for the wider popularization of Everett's theory, which had been largely ignored for the first decade after publication. DeWitt's phrase, many worlds, has become so much more popular than Everett's universal wave function, or Everett-Wheeler's relative state formulation, that many forget that this is only a difference of terminology. The content of both of Everett's papers and DeWitt's popular article is the same. The many worlds interpretation shares many similarities with later, other, post-Everett interpretations of quantum mechanics which also use decoherence to explain the process of measurement or wave function collapse. MWI treats the other histories or worlds as real since it regards the universal wave function as the basic physical entity, or the fundamental entity. obeying at all times a deterministic wave equation. The other decoherent interpretations, such as consistent histories, the existential interpretation, etc., either regard the extra-quantum worlds as metaphorical in some sense, or are agnostic about their reality. It is sometimes hard to distinguish between the different varieties. MWI is distinguished by two qualities. It assumes realism, which it assigns to the wave function, and it has the minimal formal structure possible, rejecting any hidden variables. Quantum potential, any form of a collapse postulate or mental postulates. Decoherent interpretations of many worlds using Ein selection to explain how a small number of classical pointer states can emerge from the enormous Hilbert space of superpositions have been proposed by Wojciech H. Zurek. Under scrutiny of the environment, only pointer states remain unchanged. Other states decohere into mixtures of stable pointer states that can persist, and, in this sense, exist. They are Ein-selected. These ideas complement MWI and bring the interpretation in line with our perception of reality. Many worlds is often referred to as a theory, rather than just an interpretation, by those who propose that many worlds can make testable predictions or is falsifiable, or by those who propose that all the other, non-MW interpretations, are inconsistent, illogical or unscientific in their handling of measurements. Hugh Everett argued that his formulation was a meta-theory, since it made statements about other interpretations of quantum theory, that it was the only completely coherent approach to explaining both the contents of quantum mechanics and the appearance of the world. Deutsch is dismissive that many worlds is an interpretation, saying that calling it an interpretation is like talking about dinosaurs as an interpretation of fossil records, interpreting wave function collapse. As with the other interpretations of quantum mechanics, the many worlds interpretation is motivated by behavior that can be illustrated by the double-slit experiment. When particles of light are passed through the double slit, a calculation assuming wave-like behavior of light can be used to identify where the particles are likely to be observed. Yet when the particles are observed in this experiment, they appear as particles and not as non-localized waves. Some versions of the Copenhagen interpretation of quantum mechanics proposed a processive collapse, in which an indeterminate quantum system would probabilistically collapse down onto, or select just one determinate outcome to, explain this phenomenon of observation. Wave function collapse was widely regarded as artificial and ad hoc, so an alternative interpretation in which the behavior of measurement could be understood from more fundamental physical principles was considered desirable. Everett's Ph.D. work provided such an alternative interpretation. Everett stated that for a composite system, for example a subject observing an object, the statement that either the observer or the observed has a well-defined state is meaningless. In modern parlance, the observer and the observed have become entangled. We can only specify the state of one relative to the other, i.e., the state of the observer and the observed are correlated after the observation is made. This led Everett to derive from the unitary, deterministic dynamics alone the notion of a relativity of states. Everett noticed that the unitary, deterministic dynamics alone decreed that after an observation is made, each element of the quantum superposition of the combined subject-object wave function contains two relative states, a collapsed object state and an associated observer who has observed the same collapsed outcome. What the observer sees and the state of the object have become correlated by the act of measurement or observation. The subsequent evolution of each pair of relative subject-object states proceeds with complete indifference as to the presence or absence of the other elements, as if wave function collapse has occurred, which has the consequence that later observations are always consistent with the earlier observations. Thus the appearance of the object's wave function's collapse has emerged from the unitary, deterministic theory itself. Since the wave function merely appears to have collapsed, then, Everett reasoned, there was no need to actually assume that it had collapsed. And so, invoking Occam's razor, he removed the postulate of wave function collapse from the theory. Probability. A consequence of removing wave function collapse from the quantum formalism is that the Born rule requires derivation. Since Many-worlds derives its interpretation from the formalism, attempts have been made, by many-world advocates and others, over the years to derive the Born rule, rather than just conventionally assume it, so as to reproduce all the required statistical behavior associated with quantum mechanics. There is no consensus on whether this has been successful. Everett, Gleason and Hartle-Everett briefly derived the Born rule by showing that the Born rule was the only possible rule, and that its derivation was as justified as the procedure for defining probability in classical mechanics. Everett stopped doing research in theoretical physics shortly after obtaining his Ph.D., but his work on probability has been extended by a number of people. Andrew Gleason and James Hartle independently reproduced Everett's work, known as Gleason's theorem, which was later extended. DeWitt and Graham. Bryce DeWitt and his doctoral student R. Neil Graham later provided alternative derivations to Everett's derivation of the Born rule. They demonstrated that the norm of the worlds where the usual statistical rules of quantum theory broke down vanished, in the limit where the number of measurements went to infinity. Deutsch et al. An information theoretic derivation of the Born rule from Everettian assumptions was produced by David Deutsch and refined by Wallace and Saunders. Deutsch's derivation is a two-stage proof. First, he shows that the number of orthonormal Everett worlds after a branching is proportional to the conventional probability density. Then he uses game theory to show that these are all equally likely to be observed. The last step in particular has been criticized for circularity. Some other reviews have been positive. Although the status of these arguments remains highly controversial, some theoretical physicists have taken him as supporting the case for parallel universes. In the New Scientist article, reviewing their presentation at a September 2007 conference, Andy Albrecht, a physicist at the University of California at Davis, is quoted as saying, "This work will go down as one of the most important developments in the history of science." Wojciech H. Zurek has produced a derivation of the Born rule, where decoherence has replaced Deutsch's informatic assumptions. Lutz Polly has produced Born rule derivations where the informatic assumptions are replaced by symmetry arguments. The Born rule and the collapse of the wave function have been obtained in the framework of the relative state formulation of quantum mechanics by Armando VDB. Isis. He has proved that the Born rule and the collapse of the wave function follow from a game theoretical strategy, namely the Nash equilibrium within a von Neumann zero-sum game between nature and observer. Brief overview. In Everett's formulation, a measuring apparatus M and an object system S form a composite system, each of which prior to measurement exists in well-defined states. Measurement is regarded as causing M and S to interact. After S interacts with M, it is no longer possible to describe either system by an independent state. According to Everett, the only meaningful descriptions of each system are relative states. For example, the relative state of S given the state of M, or the relative state of M given the state of S. In DeWitt's formulation, the state of S after a sequence of measurements is given by a quantum superposition of states, each one corresponding to an alternative measurement history of S. For example, consider the smallest possible truly quantum system S, as shown in the illustration. This describes, for instance, the spin state of an electron. Considering a specific axis, the north pole represents spin up, and the south pole, spin down. The superposition states of the system are described by a sphere called the Bloch sphere. To perform a measurement on S, it is made to interact with another similar system M. After the interaction, the combined system is described by a state that ranges over a six-dimensional space. This six-dimensional object can also be regarded as a quantum superposition of two alternative histories of the original system S, one in which up was observed and the other in which down was observed. Each subsequent binary measurement causes a similar split in the history tree. Thus, after 3 measurements, the system can be regarded as a quantum superposition of 8 equals 2 times 2 times 2 copies of the original system S. The accepted terminology is somewhat misleading because it is incorrect to regard the universe as splitting at certain times, at any given instant. There is one state in one universe. Relative state. In his 1957 doctoral dissertation, Everett proposed that rather than modeling an isolated quantum system subject to external observation, one could mathematically model an object as well as its observers as purely physical systems within the mathematical framework developed by Paul Dirac, von Neumann and others, discarding altogether the ad hoc mechanism of wave-function collapse. Since Everett's original work, there have appeared a number of similar formalisms in the literature. One such idea is discussed in the next section. The relative state formulation makes 2 assumptions. The first is that the wave function is not simply a description of the object's state, but that it actually is entirely equivalent to the object, a claim it has in common with some other interpretations. The second is that observation or measurement has no special laws or mechanics, unlike in the Copenhagen interpretation, which considers the wave function collapse as a special kind of event which occurs as a result of observation. Instead, measurement in the relative state formulation is the consequence of a configuration change in the memory of an observer described by the same basic wave physics as the object being modeled. The many-worlds interpretation is due its popularization of Everett's work, who had referred to the combined observer-object system as being split by an observation, each split corresponding to the different or multiple possible outcomes of an observation. These splits generate a possible tree as shown in the graphic below. Subsequently, DeWitt introduced the term world to describe a complete measurement history of an observer, which corresponds roughly to a single branch of that tree. Note that splitting, in this sense, is hardly new or even quantum mechanical. The idea of a space of complete alternative histories had already been used in the theory of probability since the mid-1930s, for instance, to model Brownian motion. Under the many-worlds interpretation, the Schrödinger equation, or relativistic analog, holds all the time everywhere. An observation or measurement of an object by an observer is modeled by applying the wave equation to the entire system comprising the observer and the object. One consequence is that every observation can be thought of as causing the combined observer-object's wave function to change into a quantum superposition of 2 or more non-interacting branches, or split into many worlds. Since many observation-like events have happened, and are constantly happening, there are an enormous and growing number of simultaneously existing states. If a system is composed of 2 or more subsystems, the system's state will be a superposition of products of the subsystem's states. Once the subsystems interact, the states are no longer independent. Each product of subsystem states in the overall superposition evolves over time independently of other products. The subsystem's states have become correlated or entangled, and it is no longer possible to consider them independent of one another. In Everett's terminology, each subsystem state was now correlated with its relative state. Since each subsystem must now be considered relative to the other subsystems with which it has interacted. Properties of the theory. MWI removes the observer-dependent role in the quantum measurement process by replacing wave-function collapse with quantum decoherence. Since the role of the observer lies at the heart of most, if not all, quantum paradoxes, this automatically resolves a number of problems. See for example Schrödinger's cat thought experiment, the EPR paradox, von Neumann's boundary problem, and even wave-particle duality. Quantum cosmology also becomes intelligible, since there is no need anymore for an observer outside of the universe. MWI is a realist deterministic, local theory, akin to classical physics, at the expense of losing counterfactual definiteness. MWI achieves this by removing wavefunction collapse, which is indeterministic and non-local, from the deterministic and local equations of quantum theory. MWI provides a context for the anthropic principle which may provide an explanation for the fine-tuned universe. MWI, being a decoherent formulation, is axiomatically more streamlined than the Copenhagen and other collapse interpretations, and thus favored under certain interpretations of Occam's razor. Of course, there are other decoherent interpretations that also possess this advantage with respect to the collapse interpretations.